Hello friends and welcome to a new lecture on linear algebra. We already learned about vectors, matrices and linear equations or a system of linear equations, and today we want to just practice more and learn more about the important topic of how to solve ax equals to b, right? Where a is the coefficient matrix. These are variables. This is a vector. And this is also a vector, which are constant terms, or we also call them as right-hand side. These equations work together to describe a relationship between the variables, right? That's why we call it as linear algebra. Algebra meaning is relationship. Each equation in the system represents a linear relationship, which means the highest constant power is 1. We don't have x squared, we don't have xn, we don't have x in power of y. These things we don't have. In today's lecture, we want to have more examples and try different ways to find solutions set of a system of linear equations. In fact, we already tried most of them, but in summary, I can say there are 4 ways in order to solve system of linear equation. One is substitution, where we substitute using another values. Then we go for elimination, then matrix, and for graph. In substitution, we try to isolate one variable in terms of other and then substitute. For example, when we say x plus y is equal to 2, we can say x is equal to y minus y plus 2, right? Then this value bring to other equation and we substitute. In the case of elimination method, we aim to eliminate one variable by adding or subtracting or multiplication with others. And here, our goal is to obtain a single equation with one variable. We want to simplify. In case of the matrix, we can go for Gaussian elimination and other things that we want to remove coefficient of others, make them as 0 or 1, then simply we can solve the others. And in graphical, I show you in the previous lecture that how to, we do plotting, and based on the plotting, whenever lines cross each other, then we say here is an intersection point. And the intersection point is the solution set. Or for example, if they are parallel, then there is no solution. Or if they overlay each other, then there are infinity solutions. We have a concept of equivalency in equations. If two systems of linear equation, they have the same solution set, then we call them as the equivalence, right? In this case, if I want to solve this one very easy using substitute, I can say x1 is equal to 3x2, right? x1 is equal to 3x2. Then I can substitute it here, then I can say 3 times 3x2 plus x2 is equal to 10, 9x2 plus x2 is equal to 10, 10x2 is equal to 10, x2 is equal to 1, right? Then if I put it here, then x1 will be 3 multiplied 1, which is 3. x1 is equal to 3, right? So here is the same solution, but in this one also the solution set is the same, right? X is 3, x1 is 3, x2 is 1, right? So these two are called as equivalent system of linear equations. Again, we want to practice again by row operations. Simple operation we define on a system of linear equation. They do not change the solution set of the system, right? Because they are equivalent, right? If we apply these things, we are generating the equivalence, as you can see here in these cases, right? So these are used for solving system of linear equations. And equivalent system of linear equation, they have always the same solution set. So we can do some elementary row operations like interchange, scaling, and row addition. In this case, these two systems of linear equation, they are equivalent. It means they have the same solution set, right? But we swap the rows. Or in this case, I just multiply the second row by -3, but still these two are same, equivalent, right? In here, the same, right? They are equivalent. And now, how to transform a given system of linear equation into another one to create some simple one. So we do it again and again until the system of linear equation is simple in such a way that we know the answer simply, right? So in order to come up from this one to this one, just we do simple row operations. In order to come from here to here, just if you look at here, this is R2, right? If I say 3 times of R1 plus R2, so I can say R2 equals to R2 plus minus 3 times of R1, right? So 3 minus 3, it will be 0. And this one, it will be 10 and 10, right? Then if I just simply divide this one by 10, it means R2 equals to R2 divided by 10, then I will have x2 is equal to 1, right? And if I say x2 is equal to 1 and I put it here, then I will have x1 minus 3 multiplied 1 is 0, then x1 minus 3 is 0, and x1 is equal to 3. So simply I found out these solutions. I transformed my linear equation system to a simple one. Augmented matrix is another solution to do this one. Augmented matrix is very easy. It's a kind of mathematical representation, and we generally use augmented matrix for solving system of linear equations, like when applying matrix methods. In the augmented matrix, what we have, for example, here is our system of linear equations, right? So we have one equation, two equations, up to m equations, and we have n variables. We have n variables, and here is the constant terms. So this a11, a12, these are coefficient matrix. This is our coefficient matrix, right? A. Then we have variables, right? Variables are a vector x1, x2, x2 up to xn, and also we have right hand side, which is b, right? So augmented matrix is like this: coefficient matrix, and right hand side. If you put them all together, then we have augmented matrix. Again, remember that two systems of linear equations are considered equivalent if they have exactly the same solution set. So strategy of solving is the same what we did already for different equations, that those are row operations. This time we will apply on matrices, right, for our augmented matrix that we have generated. And we worked again and again to finally we'll come up with a simple solution. Working with matrices is much more easier because we don't have the variables, only we have those things. So then we can come up with the sum echelon form. So what we do, these are the row operations that we are doing, row operations. This is our system of linear equation. We convert it to a matrix, right? So what we have here, this is coefficient matrix, this is coefficient matrix, and this is right hand side, right? Then we do the same thing that we did, right, by removing 1, right? So we say that if we this one minus 3 times of this one, then we will have this one, right? So this is what we did here. Then the next time, if we divide it by 10, then x2 become 1, right? So this is the same as this one. And finally, we come up with this solution. This is coefficient matrix, and this is constant term. Working with matrices is easier. A system of linear equation is very easy to solve if we use an augmented matrix and transform it to RREF, row reduced echelon form. So we have two terms here, REF and RREF. I will explain later what is the differences. So in this process, we have two kind of lines. Some lines are considered as zero lines, so these are zero lines, zero rows, and this is non-zero rows, right? Also, these are considered as leading values, right? So a leading entry that we have is the leftmost non-zero entry in a row, which is non-zero row. Then we have pivot, so these are considered as pivot. Pivot position in matrix is a component that corresponded to a leading one in the reduced echelon form. So these are leading, and it means we want to have 1 in the final form of RREF. A pivot column is a column that contains a pivot position. So we want to transform this one. We have this example, right? But conditions are in RREF always, if you have a zero row, it must be at bottom, right? The other condition is if you have leading one, the last row, which has the leading row, should be 1 column after. It means this one should be here, right? In order to do that, we cannot move this one here. But what you think if we swap R2 and R3, right? So if we swap R2 and R3, we will have 1 0 0 6 3 0. Then we will have 0 1 0 2 4 0 0 0 1 5 7 0, and all up to here 1. So you can see here these are in echelon form, right? The leading is the leftmost one. Here we have also row echelon form, and also we have column echelon form, right? So this matrix is in row echelon form already. The column containing the leading entries are standard vectors. So we want to transform into column echelon form. For this purpose, we need to take care of column number 2 and column number 3, right? So the column containing leading entries are standard, as you will see here. And if a column contains the leading entry, then all the others should be 0. So it means here we have to change this one to 0. As you can see here, we have to change this one to 0. The rest is okay, and the leading entry should be 1. So here we can have leading entry of 2, but it should be 1. So if you can see, this is called as row echelon form. This is row echelon form. This is column echelon form. How you do it? By row operations. If you follow a set of row operations, you come up from 1 to second one. Okay, I want to practice one here for you. So this is RREF. It's a kind of REF, but in here we have 1 and 0. So in RREF, a matrix transform using a series of row operations, and it first should be in row echelon form. Then, in addition to the condition that we did for row echelon form, in reduced row echelon form, all entries in each column that contains leading one are 0. And in other words, we can say that reduced row echelon form is a further enforcement of row echelon form. A matrix which is in reduced row echelon form is fully simplified and provides a very clear representation of the solution to the system of linear equation that we have. So you can see here, this is our augmented matrix, and we want to come to here. How we can do that? So this one is okay. So we have to care about this one, and we should make this one as 0. So I want to transform this one. So this is R2. R2 is -1, -2, -2, 1, 2, 3, 6. And if I say R2 equals to R2 plus R1, then what I have, this one will be R2 plus this one. So this will be 0, 0, 0, 4, 4, 4, 4, 8, right? So let me do it here. So I have 1, 2, -1, 2, 1, and 2. Then new row is this one, 0, 0, 4. Right? And the rest is the same, 2, 4, -3, 2, 0, 3, and -3, -6, 2, 0, 3, and 9. In the second line, I should take care of R3. So R3 is 2, 4, -3, 2, 0, and 3. If R3, this one, R3 minus 2R1. R3 minus 2R1. Then 2. So let's remove R3. So then we will have 0, 0, -1, -2, -2, -1, -1, -2, -2, -1, right? Then if I go for R4, so if I say R4 plus 3 times of R1, R4 equals to R4 plus 3 times of R1. So I remove R4. Then I will have this one, and this one will be 0, 0, 0, -1, 6, 6, and 15. Okay, then for this one, as you can see here, if I swap R2 and R3, then R2 will be 0, 0, -1, -2, -2, -1, and R3 will be 0, 0, 0, 4, 4, 8, right? Because this leading should be 1 after this one, right? Then R2, we have some negative here, we want +1, right? If I say R2 equals to minus R2, right? Minus R2. So it means now R2 is just, I remove this one, right? Then in the next round, if I say R1 plus R2, right? I say R1 equals to R1 plus R2, R1 plus R2. R1 now is 1, 2, -1, 2, 1, 2, right? Then R1 will be 1, 2, 1, 2, 0, 4, 3, 4, 3, and 3. Then in case of R4, we should take care of this one, right? Then I say R4 is equal to R4 plus R2, R4 plus R2. We want to remove this one, right? So R4 now is 0, 0, -1, 6, 6, and 15. If I remove this one, then I will have then so let me remove these things. Then, so R4 and R2 we did. Then we will go to R3. You can see, so R3 is equal to 0.000448. R3, if divide it by 4, R3 is equal to 1/4 of R3. So let's remove it. Then we will have 0.000011 and 2, right? Then if you look at R1, if we R1 minus 4 times of this one, R1 minus 4 times of this one, so R1 equals to R1 minus 4 times of R3. So R1 now is 120443. So R1, 1 minus 0, it will be 1. Then next will be 2. And the next will be 0, 0, minus 1, and minus 5. Then in case of R2, we can say R2 equals to R2 minus 2R3, right? So now R2 is 0.01221. After this, R2 will be 0.0.100 and minus 3, right? And if you look at this one, if we just R4 minus 8 times of this one, so R4 is 0.00816. R4 equals to R4 minus 8 times of R3. Then we will have 0.00000 and 0, right? So this is somehow in echelon form. The 0 row is at bottom and the leadings are something like this, right? Then we can simply solve these equations if there is some solution. So if we do it in reduced row echelon form, it will be easy. For example, here we have one example, and this is a very easy example. Here we have coefficient matrix, and here we have right hand side. So x1 is equal to 4, right? x2 is equal to minus 5, x3 is equal to 3. So this is a kind of unique solution and easy solution. Here is an example which has infinite solution. Infinite solution means you cannot specify all of them. In here we have a matrix, as you can see here, and based on this one, so we have 1x1 minus 3x2, 0x3, 2x4, and 0x5, and right hand side is 7. Then we have nothing. We have 1x3, 6x4, and 9. Then here we have x5 is equal to 2. If we bring these parts to this side, then we will have something like this. x1 is equal to 7 plus 3x2 minus dx4. And for this one, in here 2 is free. What is the meaning of free? If variable is free, it means it does not have a pivot position like what we have here. And the other side, we have a basic variable if it corresponds to a pivot column. In order to determine which variables are basic and which are free, it is necessary to row reduce augmented matrix to be in echelon form, right? So x2 is free here. It means any value you can get. x3 is this one. Based on this one, we got it. And x4 is free, and x5 is equal to 2, right? Then based on this one, we can come up with a generalized form, right? Or we can say parametric representation. Parametric representation, in this case, instead of giving explicit equation, parametric representation expresses the coordinates of points in terms of one or more parameters. We just bring those equations into the matrix form, as you can see here, and we say, okay, this is for the right hand side, then this is for x2, and this is for x4. So these are our free variables. These two are our free variables. We did not find the solution, but there are many solutions. We found a general form in which x2 and x4 can get these values. The others we can do based on these x4 and x2. Let's see one case which has no solution. We can see that this is inconsistent. So an augmented matrix contains a row in which the only non-zero entry lies in the last column. Meaning in the original system of linear equation there are contradictions. So what it means, in here we have x1 minus x3 equal to 0. We have x2 plus x2 is equal to 0 is okay. But here we have nothing but equal to 1, means all are 0, right? 0x1, 0x2, 0x3. So this is contradiction, and we can say it is inconsistent and there is no solution. Gaussian elimination, as we saw already, is another form of transforming one matrix to reduced row echelon form. The Gaussian matrix came after Carl Friedrich Gauss from Germany. He has proposed this one. So in this case, we do two ways as we did so far, forward pass and backward pass. In forward pass, we go to the row echelon form, and then we can go to the row reduced echelon form by substituting and making them easy. So you can see here x3 is equal to 3, x2 is equal to 5, x1 is equal to minus 4. Whatever we did so far, we did forward and backward. We try to simplify this one, then we substitute and find out the variables. In forward path, the goal is to convert the original matrix into upper triangular form, which is in row echelon form, and in backward, we refine the matrix of the row reduced form, and we try to simplify it by substitute. So here is one example to better understand the topic. So here we have 3 equations and 3 variables, right? So again, we bring to augmented matrix. So you can see here, it will be something like this, right? So look at here. If I say R2, R2 is equal to R2 plus minus 2R1, right? It means I want to make it 0, right? So then I will have something like this. Then in terms of this one, if I say R3 plus R1, so it will be 0, as you can see. And for this one, if I say R3 minus R2, then it will be something like this, right? This is not in row reduced echelon form, but it is in echelon form. So in this case, what I have, I already found z, right? Because 4z plus equal to 8 and z is equal to 2. If I bring it here, I will have y plus z is equal to 4. I already have z equal to 2, y plus z is equal to 4, and y is equal to 2. 9 is wrong. Y is equal to 2, and if I substitute here, 2x plus 4 multiplies 2 minus 2 multiplies 2, then it gives you x is equal to minus 1, right? In this way, we can do forward and backward. This part is called as forward, and this part is called as backward. So we found that x is equal to minus 1, y is equal to 2, and z is equal to 2. The row picture has 3 planes from 3 equations. All the planes go through the solution. The original planes are sloping, but the last 4z is equal to 8 will be something horizontal. This is called as column picture. Right? Minus 1 is x1, 2 is xy, and this one is z. Then we can present it in this way. You may have several results for REF. We have multiple REF, but we can have only one RREF. RREF is the solution, you can say, you know, because in here x1 will be minus 4, x2 will be 5, minus 5, and x3 will be 3, right? It means already solved. Okay, so this was to help you to better understand the topic, and please feel free to ask me if you have any questions. Thank you.